Okay, so yeah, my name is Joe Savona. I'm a software engineer at Facebook, and I work on the Relay team as well as working with the GraphQL teams for building our native clients on iOS and Android. So I've been at Facebook for about 2 years, so I haven't been there for the entire history of our GraphQL client development. So in kind of preparing for this talk, I've looked at what we've done in Relay, as well as talking to a whole bunch of people around the company and kind of getting more information about the early years of GraphQL, just to make sure that I'm kind of covering all the bases. So at Facebook, we've been developing GraphQL clients for over 4 years. And in this talk, I want to share about the lessons that we've learned. So let's start by answering the question, what is a GraphQL client? I mean, I think we all have like an intuitive sense of what it should do, but let's kind of just nail down the specifics of that a little bit. So a GraphQL client allows developers to specify queries. Obvious. It sends those queries to the server. It parses the responses that it gets back and makes the parsed objects available to user interface code. So far, so good. It should also cache data that's already been fetched to avoid refetching data unnecessarily. And also, by caching data, we can allow the application to work offline. It keeps the data and the UI consistent. So if we've fetched a particular piece of information once, and that appears in multiple places in the user interface or in a cache, and that data changes, that change should be reflected everywhere that piece of information is displayed or cached. A GraphQL client should make it easy to fetch paginated lists. So things like the Facebook newsfeed or a search results list, where there may be many more items than we can download at one time. There may be algorithmic ranking, things like that, and we want to be able to fetch lists incrementally. And finally, a client should allow us to execute mutations. And the mutation system should integrate with our caching and consistency approaches, and also with pagination as well. So let's start at the beginning and kind of add things incrementally as we go. So before we can even send a query to the server, we have to actually define the query somewhere. And we've seen some approaches in earlier talks of using code to generate queries and things like that. So the pattern that we've converged on at Facebook is what we refer to as colocation. Again, we've heard a lot about user interface components today. And at Facebook, we've developed React, component kit for iOS, and of course we can use Android views as well. And so the pattern that we've developed is to either have a .graphql file that contains fragments for each component, or have the GraphQL embedded in the code. In our JavaScript client Relay, we actually embed the GraphQL directly into the JavaScript. In either case, this makes it a lot easier to keep the data fetching and the UI in sync. Again, we've kind of repeating some things we've heard today, so I'll move through this a bit quickly. But in general, this allows us to, if we add a property to the user interface, so if we're adding a name that wasn't there before, we can then jump directly to the fragment, add that field, and keep the component in sync with its data dependencies. This also means that if we reuse a component somewhere else in our application, we can simply reference its fragments and make sure that we've fetched all the data to render that UI. By kind of avoiding, it's really tempting, I think, to create shared fragments and have some user fragment that we reference in multiple places in our application. But this means that if we might have some field that exists in that fragment, and now we have to go and check everywhere that uses the data from that fragment to see, can we actually delete this field? And so by having shared fragments, it kind of defeats some of the benefits of GraphQL in that we don't get this clear association of fetching exactly what we need for a particular piece of code. Okay, so colocation has worked out pretty well for us. Now let's look at query construction. Again, we saw some approaches to this before. So a kind of first pass at doing query construction would be something like what we do in the current version of Relay. So this is at build time. We can look at the query string on the left. Again, I've put quote marks around it to emphasize the fact that this is a text string. And at build time, we can just do an initial parse of this and create a simple AST representing the query. This is how Relay works today. So this works, and the object representation allows us to describe things like when we have a fragment reference, so the ... photo, we can generate code to actually look up the actual code representation of the photo fragment at runtime. Now at runtime, we can take this AST, execute it, embed fragments into their parents, get one giant representation of the entire query, print that to a string, and send it to the server. This is very much like the approach that we saw earlier from Shopify. So this works fairly well for smaller applications, but it doesn't necessarily scale. So as our product grows in complexity, we're going to add more UI components. We're going to add more different types. So we might have had a story type before, but now we might have a photo story and a video story, and all these different variations. And so our queries grow larger even as the amount of data we're fetching doesn't actually grow as much because we have unions and more complexity and more fragments. So over time, as you can see from this completely non-scientific graph, our query size will grow, right? And the thing is, this isn't just the query size. The query size actually has an impact. It means that we're spending more time at runtime just simply generating the query representation and converting that back into a string. It means we're taking time. Every single user of our application has to wait while their phone is doing all that work, uploading all those bytes to the server, and every time they run the app, they're uploading the same bytes over and over again. And that means that the time spent uploading is time that they're not spent downloading the response and actually using the application. So again, this isn't necessarily a problem at first, but it can become a problem, or it may become a problem over time. So one option that you might think of is, okay, well, let's just stop doing collocation, we'll write super minimal optimized queries. You don't have to do that. There's an alternative. That would kind of throw away the benefits of collocation, and the alternative that we've arrived at is what we refer to as persisted queries. So going back to that build time step, we already have a clear structure for where to define the queries. So we know where to look for them. They're in either .graphql files or they're embedded inside the code. And we already have a mechanism to actually convert from these disparate collocated fragments back into an AST and convert that AST into query text. We're doing that exact work at runtime. The key insight is that we don't actually have anything happening at runtime we're not dependent upon a runtime to know what the query is. These are all just static pieces of text around our code base that are just getting put together at runtime and sent to the server. So we can do that query aggregation at build time. So we can take all those different fragments, put them together, send it as text to the server, again, in a build step. Save it in a database, assign it an ID. We can hash the query text to get the consistent ID, and return that back to the build step, and then save that ID somewhere. Now, at runtime, instead of sending up this massive query string, we can send the ID and just the variables. So if, for example, you wanted to have some conditional logic, in certain cases we'll fetch this fragment, other cases we'll fetch this fragment, we can just use an @include or @skip directive and then send a variable at runtime to choose which one we fetch. And then we can get the data back and render. So now, returning to our completely unscientific graph, we can see that persisted IDs don't get larger over time. The main thing that changes here is we're probably going to add a bunch of variables, and so the amount of data we send in the variables will grow, but this is much more scalable. So persistent queries have been working well for us. Effectively, all the queries in our iOS and Android clients are persistent IDs. I say effectively because I admit the possibility that there's a text being sent somewhere, but I think in practice, yeah. So, and in Relay, we are not using, the current version of Relay doesn't support persistent queries. We're moving toward supporting them in our JavaScript client as well. Some ideas, if you use persistent queries, are it can be helpful when you're debugging a production issue. You probably have the ID that the client sent, and so it's helpful to have a quick, an internal tool you can go to quickly get the query text for that ID. You may also want to be able to have put in the query name and get back the list of IDs that have been assigned to that query, so I can see all the versions of the feed query over time and what is the current ID that's about to be sent to master. The other thing you might want to do is to actually log the performance. So we saw some tools that allow you to log performance characteristics, and persistent IDs kind of give you a really great way to do that. So you can, for example, see, okay, let's look at the performance of the feed query over time and see how each different ID worked and how many times that ID is actually being used by clients. So far, persistent queries give us a way to efficiently fetch a new query that we haven't already fetched before. But as we can all imagine, we're probably going to want caching. right? We open a screen on our app, we leave that screen, a few minutes later we come back, and now we're stuck downloading all the data for that screen all over again. Ideally, this would be fast, and we can use the data that we fetched a few minutes before. So again, this is a really specific use case, and this kind of goes to our development philosophy for our clients, which is to try to solve specific use cases first, see whether that works, and if it does, great, and if it has problems, then we solve the next problem. So just like with REST or other HTTP protocols, we can just simply add a response cache. So here we'd have a kind of read right through cache where we have a mapping of IDs and variables. We kind of do like a stable hashing of those to get a key. If that key is already in the cache, we just use the cached value. Otherwise, we go to the server, get the data, put it into the cache, and then return it to the UI. Standard things apply here like TTL, so some form of expiration so that we don't keep cache data around for too long, and all the things about LRU or other eviction algorithms, putting a maximum cache size. One other thing you can do is to persist this cache to disk so that if the user is offline, they can still actually maybe get the initial screen's worth of data, for example. It's kind of an easy and cheap way to get some amount of offline functionality. Okay, so a response cache is really useful, but it introduces its own problems. How do we ensure that data is actually correct? And how do we ensure that it's consistent? So let's look at an example. Imagine that we fetch a query that includes the message count. So if you're familiar with Flux at all, you'll recognize this example. But so we fetch the message count at a certain point, and we cache the value for this, and the message count is 1. At some other point a bit later on, we fetch a different view that also happens to include the message count. And at that point, the message count is 2. If we cache these results independently, the two caches will now have different values. And if we were to go back to that previous screen, we'd use the cached value, and we'd see message count 1 in one part of our app and message count 2 in a different part of our app, and that's not necessarily a great user experience. So without some form of coordination, these two cached values will get out of sync. So we'll need something to coordinate these. There's a lot of different approaches to this, kind of more decentralized approaches, more normalized. The approach that we're kind of converging on in our clients, in particular on our in Relay and in our iOS client today, and kind of moving towards, I think, on Android, is to have a more normalized store. And that sits kind of at the center of the client-side cache. So every query that we fetch is published into the store. And then views subscribe to a query and pull the latest values of that query from the store. So in the case we saw before, when we fetch a subsequent query, not only do we see the new count on the new view, but because that data is published to the store, which then gets notified and published to the previous screen, they now both get the correct message count. The format of the store is basically a flat mapping of kind of identifiers to records, where a record is another mapping of basically field name to value. And so here, for example, you can see that we've got a store that has 2 entries in it, my ID, where the identifier might be the type user and then my actual ID, kind of put together as the identifier. We have a record, we have the type name, we have the ID field, the name, and then you can see that for a city where I live, we're not actually encoding the record directly. We have a reference to this object by its ID. And so this allows us to have a flat mapping where we can take in a new set, we can basically take a new store and an old store, kind of walk them together and just merge the two together. So the main kind of operations that we have on the store are publish, where we have some new data we've gotten from the server, and we have existing data in the store. We take those two mappings, walk them together, add any new entries from the server, and just simply add them. If the record exists in both, we merge them together. And as we do that, we can record which IDs have actually changed. The other side of this is to subscribe and notify. So a UI subscribes to the store with a query or a fragment. And when new data is published, we look at the results, what changed in the store. So we know that ID A was added, ID B changed, ID C got deleted. And we can look at the subscriptions and see which subscriptions would be affected. And any subscriptions that are, we basically re-execute the query and give the new results back to the UI. So components only kind of get the actual records that they need, and we avoid unnecessarily updating UI. So if your query isn't affected by a result, you don't get notified and you don't have to re-render. So there are some kind of trade-offs to consider here. It isn't quite as simple as just making everything automatically consistent. For example, we may want to delay the publish. So imagine that we're on a mobile phone and we navigate to a new screen. The user can only see the new screen anyway. So we might want to prioritize rendering that new screen before we update any other screens that the user can't see right now. And so we're kind of having some amount of eventual consistency. Technically speaking, that screen is not consistent, but we can't see it, so that's okay. Also, there may be certain specific cases where we actually want to opt out of consistency. It can just happen in your product where you have a specific case, like maybe the user's interacted with some data already, and if I've already modified one field, I don't want the other fields in the form to change. Certain edge cases like this can happen. We can usually handle them by just letting the store notify you and just ignore the new notifications that you get, but it's something to consider. And then finally, lists are fetched incrementally. We fetch a first part of a list, a second part of a list, and it isn't quite as straightforward to automatically make lists consistent. And moreover, if I've scrolled down in the comments for a story over here in the UI, I probably don't expect comments on some other part of the screen to suddenly start scrolling as well. Users kind of expect that different instances of a list are actually distinct. So we'll need a solution for that as well. So let's briefly return to caching. So far we looked at just simply going to a screen, going away, and coming back to that exact same screen. But there's another case that can be pretty common. So and that's where we have a list view, and then we click into a detail view. This is very, very common in applications. So for example, looking at my news feed, and we have a lot of information already on the client about this story that I wrote about the GraphQL Summit. If I click on it, I'm going to see a loading spinner because our response cache doesn't have this query yet. But ideally, we actually have a lot of data on the client. We could use that to more efficiently, to more quickly render this screen and maybe fetch just any missing information in a separate query. Now, we looked at the notify operation where when new information is published, we kind of tell the view what's changed. Well, implicit in that is the ability to execute a query against the cache. So we're used to basically having queries be executed on the server where the resolve function is calling your product-specific business logic. But in this case, the resolve function is the very, very simple lookup in this, in this normalized map. And as we go down fields, we just continue to look up references. So for the case that we just saw of navigating to a details page, we can look in the store and just traverse the query. Do we have everything for this story? So we'll start at the top of the query, look in the cache, and load the story ID. Okay, it's there, great. Now we can traverse down to the author of the comments and continue down executing the query to see if we have all the records. If every single record is in the cache, great, we have all the data we need, we can render. If we're missing anything, okay, now we'll have to go to the server and fetch that. So I mentioned that there are some kind of tricky aspects to data consistency and pagination. So there's a few things to kind of keep in mind with pagination and some use cases that we have to work around. First is that lists often need to have they express relationships. So for example, my friends list, it's not just a list of users, but it's a list of information about when I became friends with people, how I became friends with them. Those are all properties of the relationship and not either person. So we want our schema to kind of give some space for that. Lists are often ranked by an algorithm. So for example, the Facebook newsfeed. The item ordering may change over time. So for example, a story that is relevant to me today might not be as relevant tomorrow and shouldn't appear as high in the list. So if I refetch the same exact arguments, even like in a very short time span, I might see different results. And finally, with these types of lists, there's too many items to download in full to the client, and so we typically fetch them in increments. So effectively, there's this virtual list that exists in abstract on the server, and that we're going to construct a client-side representation of, but it's not clear that we'll ever have exactly a one-to-one mapping between this theoretical virtual representation on the server and what we see on the client. We're always kind of synthesizing a view on the client. So let's look at an example of that. The way that we can represent paginated lists, or what we, in Relay we refer to them, really in general at Facebook we refer to them as connections, is as a segment. And the segment says kind of where it starts in this virtual list, how many items are there, and whether there's more going in that direction or not. And then, of course, the edges themselves. So we might have gotten items A, B, and C. Now, let's say we scroll down and we want to load more items. So we'll go to the server and say, okay, well, we want more things after C. And again, I'm using after here because these are the kind of arguments that that are in the Relay connection spec, and that these are the kind of arguments that we use for Facebook for connections. You can imagine doing a very similar thing with with a limit or offset style approach. So okay, we get our new segment. So after C, we've got three more items, and there's still more things in this direction. So we have this theoretical. We have these two segments that we have to join together in some way. Right? And so the question is how. And you'll notice that I've thrown in C twice in this list because items can get re-ranked, and now maybe C is a bit less important and moves down in the list in between the time that we fetched the first set and the second set. So this is a product-specific decision. What do we do here? Do we have like C twice? Do we leave it where it was? Do we move it down? This is kind of up to you. If you've already rendered that first view, you might not want to have an item in your list suddenly jump to somewhere else. The user might be looking at it right now. And so this is something that you have to decide at the product level how to handle. There's kind of two main things you could do here: is leave C where it was originally and just ignore the second one, or move it to the new position. And so the way that we represent this typically is as kind of three levels. There's this segment, which is a chunk like this that has where it is, what edges are there, and then there's a sequence of segments because we might fetch the beginning of a list and the end of the list. And then finally, we have the connection controller. And this is a controller in the typical MVC controller sense of the word, in that it coordinates between the fetching data from the server, putting that data into the store, and allowing the UI to efficiently render the view that we've synthesized on the client. The controller can do a lot of that work automatically by having a consistent, connection scheme with a consistent naming pattern for fields and their arguments. But we'll also probably want some amount of product-specific logic, like we talked about, for how we actually merge new edges. Do we leave them where they are? Do we reorder them, etc. And for things like React or Component Kit, where we have a more declarative UI architecture, we can create a connection component that takes a configuration and a simple function to basically render each edge, right? It's going to render a list for us, and it's just going to call this render edge function once for every item. When we fetch new items from the server, it will call this function appropriately to actually render those into the UI. And the configuration can specify things like, what is the query that we use to actually get more items? What are the default variables to use? The logic for merging new items into the list, things like that. Okay, so this brings us to the last major segment, which is mutations. And remember, mutations can be really simple. It might be as simple as toggling a Boolean, but they can also be very complex, where we're adding a new item that should appear at the top of one list, but in some other part of the UI, that list is sorted in a different order, and so the item should appear somewhere else. We have to integrate with caching, etc. So the other thing with mutations that can be complicated is that a given change in the input can affect a very large number of items in the output. For example, if you and I become friends, well, you should show up in my friends list. Theoretically, my newsfeed should maybe now show stories that come from you, because your stories are now eligible to show up there. Similarly, if I block a user, then I can't see you, anything, things I have cached about you might disappear, etc. So there can be certain types of changes that really invalidate a wide part of the graph. Also, there's complex business logic and privacy that make it sometimes hard to even figure out on the client how to even emulate the results of a mutation. And so it's definitely pretty complex. So in general, just mutations are a bit harder to work with than queries, because of all these effects. But kind of even more simply, there's the question of, when I do a mutation, what do I refetch? How much do I refetch? I might have fetched a large amount of the graph, but I have to make a choice. Do I eagerly fetch everything that could change? So here's an example of a story like mutation, where I'm just clicking the like button on Facebook. What do we refetch? Well, there's a bunch of things that have the word like in them that are fields and that are obvious candidates for things that I might want to refetch. Like, do I like this story? Yeah, I'm toggling the button, so that's probably a good one to fetch. The like count, how many times it's been liked. Like sentence, kind of summarizing who's liked this. The list of people who've liked it and the name for each one, and possibly many, many more things. But the question is, do I actually need all of those fields? Well, maybe my UI is only showing the blue button, and it just needs to know whether I've liked the story or not, and all I really need is does viewer like. Maybe I'm showing a UI where I'm showing the names of people who've liked it, and so I am going to need liker's name. Maybe I have a really complicated UI that shows many, many more details about each person who's liked it, and I need way more information than just the name. So this really depends upon what you're actually rendering. So there's kind of two main options. One is to reuse a fragment that you've defined. You probably have a couple fragments in your app that are like high-level story components, and the simple thing to do would just be to reference those fragments and fetch everything you need about a story again, just to make sure. It's pretty simple. It gets you kind of in sync. There's no way it's much harder to have a piece of information be out of sync. On the other hand, there's a lot of things about a story that don't change, and then we're going to end up refetching them. So a more optimized approach would be just explicitly list out, for example, just the one field that we know we care about and that could change. And so you can kind of find a balance between these two approaches of, on the one hand, erring on the side of keeping everything consistent with some overfetching, or attempting to be more efficient and minimal. Now, this is the only slide that is in inverted colors because this is an example of something that we tried and that we've learned doesn't necessarily work as well. So we just saw how it's kind of hard to figure out like exactly what we should refetch in our mutation. And we had this thought a couple years ago, which was, what if we could infer the mutation given the things we've already fetched? To make that a little more concrete, let's look at an example. So this is how mutations work in Relay, which is where we tried this experiment. On the left, we have the fragments that we've fetched about a story. And so in reality, our application has actually fetched does viewer like and the names of people who've liked it. On the right, we have what we call in Relay the fat query. These are all the fields that could theoretically change about a story given this mutation. So does viewer like count, like sentence, likers. And I put question marks under likers because we just know that the likers could change, but we don't know what properties of them the UI would actually care about. And so we tried this experiment with Relay where we basically said, okay, we'll record these queries over time as the application is fetching information from the server, and we'll let the user define this mutation. So this is user defined, and this is stored by the system. And we'll basically intersect them. And so we'll see that does viewer like appears in both. Okay, we'll keep that. We see that like count and like sentence aren't used by the application, so we'll skip those queries. And finally, we'll see that the application has queried just liker's name, and so we'll populate the liker's field with just the name. So this seems really convenient because I can just define everything that could change, then the application is going to construct this super minimal efficient query for me. But we've been here before, right? We talked about this at the beginning of the talk. Query construction time goes up. System complexity, we have to keep all these tracked queries around. That takes memory, that takes logic in our actual client. And of course, it means we can't do persistent queries. We're stuck in sending query text up to the server. So what we kind of found is that this really seemed like a developer experience win because it lets the product developer not have to think so much about the exact right fields to fetch, but it isn't really super predictable. We look at our fat query and we say, oh, these things will probably be fetched, but you don't actually know at any given point in time which fields are being fetched. It introduces client complexity. It just makes the client have to do a lot more things. It has to do query construction at runtime. It has to keep track of those queries. It has to construct valid mutation queries, which can be, you'd think it would be easy, but it's actually not, as there's kind of some edge cases that we've run into. It means we're doing runtime query construction, and it means we can't do persistent queries, which we found to be helpful in reducing query time. So this is an example of something that we really thought would be a great developer experience win. It's really seemed intuitively like a good direction, and in retrospect, like this is something that didn't work out as well as we hoped. And for Relay going forward, we're moving back toward static mutations, which is what we're doing and have been doing on our iOS and Android clients the entire time. So I bring this up as kind of an example of how I think intuition with GraphQL clients can be tricky. It's very easy to imagine like a theoretical ideal of how a client should work, but in practice, it's better to kind of focus on a specific use case and just solve that one at a time. And I think that this is one of those ones where we're a bit optimistic about, oh, we can make this thing great, and we have like a really good idea, and it just didn't quite work out as well as we hoped. So to recap, we've tried a lot of ideas over 4 years with GraphQL clients. Some worked. Persistent queries is a great example of something that has just been fairly successful. And we've also had a few missteps, things that didn't work out as well as we hoped, like tracked queries. So the takeaway for me, and I think, and I hope for all of you, is that it's really helpful just to focus on specific use cases. Like with caching, if we don't have too much data consistency concerns, we can start with a simple request-response cache, solve a specific instance, and then move on to solve other things as we see them. Another takeaway is to exploit the declarative nature of GraphQL. So GraphQL allows us to express the data dependencies in a static text form, and that we don't need anything at runtime to generate a query, and so we can actually use that to persist queries at build time, to generate optimized artifacts based on that query. We can even generate optimized parsers to handle a response, for example. So what's next? I think it's natural that GraphQL is still kind of has only been open source for about a year. We're all kind of still in like the exploratory phase of like what is the right way to build a client. And I think a lot of the community is still trying out ideas. And so I hope that this talk has helped kind of establish a vocabulary for some of the core components within a GraphQL client system, and that allows us to kind of have more effective discussions as we talk about common components, and also gives us kind of a collective base for where to start exploring with new things. If you have questions, check out graphql.org, check out the Relay website. Thank you very much.